The last time a really good question was asked. One of the questions that was asked last time was, what do you do when you have a part or body that is loaded such that there are more than one stress component happening at the same time? And that is the question that we are going to try to answer today, at least, a technique to use for certain cases. That question can actually get pretty hairy, depending on a lot of things, but depending on things like whether the different loads that are applied to the body are in phase with one another, whether they're at the same frequency as one another, and these are all different things that can happen here. So what I want to kind of do is get that question bracketed a little bit, kind of come up with what the different possibilities are for how parts could be loaded, and then I'll show you a technique that we can use for one of those cases. Does that sound good? All right. So let's look at a scenario where we have let's say, just a cantilevered rod sticking out of a support somewhere, and let's say that this cantilevered rod is subjected to simultaneous torque, and that's going to be as a function of t because it's going to be something that varies over time. Let's say that it also has a transverse load applied at its tip, right? And so maybe I'll call that F, maybe F1 of t, something like that. And I tell you what, I'm actually going to change the color on that one because I want this to sort of code with a few of the possibilities we could have for how these get loaded over time. So I'll change that one to green. At least I will try to do that. Okay, this one's going to be green, F1 of t. All right, and then the last possibility, because we generally have torsion, we have flexure, and then we have an axial load as well. So let me code that one sort of in orange. All right, so these are our basic, these are the types of load that we see happen on parts on a fairly regular basis. All right, and many, many types of load can be boiled down into these three different categories. And we've actually already dealt with equations, and we've even done example problems in here for each of these possibilities: flexure, torsion, and axial. Okay? So let's look at what happens as we apply loads on here, and these loads now start to create stress as a function of time. I'm going to show you the first possibility is, what if all loads are in phase, okay, meaning that their maximums and minimums are in phase with one another, right? As the maxes line up with each other. Okay, the extrema of the thing line up with one another. And what you will see in that case is that the stress that we could have, we don't necessarily care what exactly this is shaped like, but let's say that this is the stress that's generated due to the torque here. So that's like a torsional stress that happens right there. Let's say that we also have an axial stress, and its peaks are lined up in such a way as they are in phase with this. They don't have to be in any other way related to the magnitude, but it's in phase and at the same frequency. That's another thing I should probably put here. Same frequency. Okay, and then the other possibility is we could have some flexure. Right? So let's say that the flexure creates a stress profile that is, in some way related, something like this maybe. Okay? And what you see there is that the extrema of all these different types of stress all line up with one another. Right? And that only happens consistently if they are at the same frequency. Right? Where it always will line up. And you might look at that and think, well, man, that seems like a very special case. Okay? Let me say this. It's not as special as you might think. because sometimes you can have all three of these different kinds of stress being applied as a result of just one load. All right, and we'll see an example that's something like that. That's what our example is going to look like today. But you could have a single load, and if this thing had, say, a dog leg on it, and you had a single load pushing in the right direction on that little dog leg, it could create torsion, bending, and axial stress all with one load. In which case, if you just had repeating some sort of a fluctuating load happening on that one point, it creates all three of these stresses, and they will be in phase with one another. Does that make sense? So this is one of our possibilities, and by the way, this is the one that we have some equations for in the book, and we're going to use those equations for our example today. Those equations, I'll just write them down right here. They are 655 and 656. Okay, well, let's look at another possibility. Another possibility is that the peaks don't line up. Okay, it's possible that you could have, some stress that's due to the torque. So it's like a pulsating torque that happens on there, and it creates this shearing stress over time. You could have some bending that happens, but the bending might be happening such that the peaks are not lined up, right? Something like this. So it's roughly the same frequency, but the peaks are not lining up. And we could do the same thing for axial here as well. Those peaks might not line up either. Something like this. Well, what do you do in this case?
What did you say this case is? Like the word stop? Like the other one?
Okay, yeah. So this is basically, this is same frequency, but out of phase. Okay, that means that the peaks of these waves don't actually line up with one another, right? And so where you might have your worst case in terms of bending, that might not be where you have your worst case in terms of torsion or the worst case in terms of axial. And so what they recommend, they actually give a strategy to approach that with in the textbook. They basically say what you should do is go ahead and combine all of these stress waves together as a function of time, right? You actually combine these things together using von Mises calculation, right? Which isn't actually that hard to do for a situation like this. Your bending and your axial loads will both create stresses in the axial direction, right? Does that make sense? Both for flexure as well as for axial, those are both creating stresses in the same direction. So you have one component of normal stress that is created from those two, and then you have a component of shearing stress that's created over here, and you combine those together. Actually, right above equation 655, they give an equation that doesn't even have a number, but it shows you a reduced form of the von Mises stress equation that you can use to find von Mises stress. And you can do that in terms of time. And as you do that, if you step through time, you can figure out where your extremes are after having combined them together. And once you do that, then you'd use their same approach that you've used in the past and find your maximum stress, your minimum stress, and then from those you can find your mid-range and alternating stresses. Okay? So that's actually not one of the ones that we're going to deal with today, but that's they give you a strategy on how you can approach it if you have this case where you have the same frequency for all your different loads, but that they may have peaks that are out of phase. Okay? Now here's your last possibility. The last possibility is different frequencies. Okay? And this actually also encompasses the possibility of extremely variable frequency, right? You could have frequencies that don't stay constant over time, right? Which means that you might have something where your torsional stress might be at a very low frequency, right? Something like this. Your bending stress might be at a really high frequency, right? Maybe something like this. And let's say that your axial is at some different frequency. So your axial may be doing something like this. So how do you handle something, a situation where everything's at different frequency and maybe they even vary? They may not stay at the same levels. What do you think you might do there? Okay? It's kind of like that. Basically what you do is you say, all right, most of the time when we're designing for infinite life. And once you want infinite cycles, right, then that means that you can sort of ignore the rest of this and imagine that there will be times where all the peaks do line up. They may not happen as frequently, right? So in this case, I'm trying to find a place where that might be close to happening, like maybe somewhere right in here, right? You have all those peaks that are close to lining up with one another, and so you'd imagine that that might be a place where you'd have your maximum amount of stress, right? And then you have another place where they might all be minimum, right? And that effectively sort of brackets the high and the ultimate high and the ultimate low stress that it might experience as a function of time. And so you just add those together, add the effects of them all together, and if you're designing for infinite life, then you can use that as a guideline. Does that make sense? So this is actually, even though it looks all complicated, it's not actually that bad because you just make an assumption here that at points in time, all of those peaks will tend to line up with each other, right? If they're at just random frequencies, they'll just accidentally sort of line up with each other sometimes in an infinite time frame, okay? So these are the different possibilities, and like I mentioned at the beginning, where we're going to put our effort here is where we have them, all the peaks that are in phase, and we are going to have them at the same frequency. Okay? And here's the actual problem that we are going to solve. All right, this is basically a little rod that is attached to some fixed wall here at A. It has a little fillet radius that helps it transition from that wall into this rod. The rod has a 0.4 inch diameter. It then bends by 90 degrees and goes downward. And each of those legs is 3 inches long. Okay? At the end of the downward portion of this rod, there's going to be a connecting rod attached using a pin. So that means we're not going to add any moments there at the point where that's connected. Okay? And maybe this is connected to some sort of like a pneumatic or a hydraulic actuator that's creating a force as a function of time on this thing. And let's say that you are able to monitor how far point C moves in response to the load that is being applied at point C. Does that make sense? A way that you might be able to do this, and by the way, this is actually not an uncommon thing to do in real life. Set up something like a dial caliper or a dial indicator, rather, such that you are watching how far some little part of a piece of machinery might deflect in response to the loads that are being applied within it. Okay, so we're getting that maybe when it sits still, right? Let's say the machine's not running and we assume that there is zero force happening in this rod. That is this middle line right here. Okay, and off of that equilibrium position, we are able to measure that it deflects by 1/10 of an inch in one direction and 2/100ths of an inch in the other direction from that equilibrium position. So far, so good? All right. And so what we want to do is, using that piece of information and the fact that we know what kind of material this is a 1050 cold-drawn steel. The properties for that are on page 1048, and I've gone ahead and pulled those out and listed them over here to the side. We have the ultimate strength, yielding strength, modulus of elasticity, and the modulus of rigidity. Okay? And what we want to do with this is find our factor of safety against fatigue using the ASME elliptic criteria. All right? Clear enough? Where would you like to start?
Free body diagram.
Free body diagram. All right. Oddly enough, I'm not sure we really need one on here. We probably can do this one without one. I know that's almost like sacrilege for me to say that, but we could probably do one without that necessarily. Here's where I frequently start. I frequently start by finding our stress concentration values. Okay, those usually don't depend on a whole lot, right? You don't have to find other things first, and usually a whole lot depends on them. And so I'm going to go ahead and start with that part of the problem to go ahead and get that part knocked out. So, and we are going to have stress concentration factors that apply where this rod goes into the wall right here. Okay? So stress concentration. All right, to do stress concentration, what do we need? Okay, we need some graphs out of the back of the book. Because I just happen to have these over here, it really comes in handy. Okay, it's crazy how some coincidences are very helpful in life. What is it that we need? So this is for the flexural part of this, and probably a comment I should make there is that this rod experiences both twisting and flexure at the point of support. Okay, you imagine this, it's experiencing twisting due to the fact that this rod is attached to this lever, and that creates a twisting action around AB. Right? But what else does it experience? Yeah, it also experiences a flexure, because we can kind of imagine this cyclic load of F sub t, you can sort of imagine it not being applied down here, and instead imagine it being applied right here, okay, in the same direction as it was, along with what else? Okay, along with a twisting action that happens around that rod. Right? And what would that twisting action, the actual magnitude of that, what would it be? Yeah, it would be that F value, which is a function of t, times the length of that moment arm, which would be 3 inches. Okay? So we kind of got a little bit of a start there on analyzing what's going on with this rod. But by replacing our original load with this load setup, it allows us to visualize what kinds of stresses are probably going to be induced in rod AB. And where do you think the worst case is going to be? Where's the critical location going to be? Yeah, probably right up there at the wall for a couple of reasons. One, that's where our moment is the maximum, right? And also we have a stress concentration there. So, that's a pretty bad place right there where it comes out of the wall. And that's where we are going to analyze it. Okay? So, when we go back over to this chart over here, we actually have two different ones. The one that I'm showing here is the one for flexure. This is the one where you have a bending moment being applied to a round rod that has a reduction in diameter. Okay, I actually have another one over here. This is the one where you have twisting happening on a rod. And so these are the two that we are going to need to use. What do we need to know to use this one? Okay, a ratio of diameters. All right, so we run into our first kind of sort of problem. What problem is that? We are not given a capital D. Okay, the presumption, or kind of what you're expected to see this as, and I didn't draw it this way because it makes it harder to notice, but there is no outer diameter. It goes into this sort of infinite wall, right? And that's what's supporting it. So what do we do? Okay, what we do is we say we are given this chart, and what we notice on the chart is, if you look at these numbers, there's a bit of difference between each of these curves, but the amount of multiplier that happens between each one of them sort of is increasing. It's a factor of 2 between that last one and this one here. And actually what happens is, as that capital D gets larger, there's less and less and less of a deviation from, where you have, an actual curve there. And so my advice to you as far as estimating these things, if you end up off of the chart, right? You want a curve that's not there, right? And not only that, but you want a curve that's not there, and there's not another one on the other side of it. So even interpolation would tend to fail, right? Now you might argue and say, well, you could extrapolate, right? And that's, yes, maybe. But what my advice to you is just use whatever the closest one is, right? So whatever the one that ends up largest of that capital D over D, just use that, okay? So for our problem, we're going to be on that capital D over D equal 3. Well, what next? Okay, R over D, which means you've got to go back and look at it again. What were those parameters? The radius was 0.03 inches, and the lowercase d, the diameter of the actual rod, was 0.4 inches. Okay, so 0.03 over 0.4 is equal to 0.175. Excuse me, 0.075. Okay, so that gives us what we need. 0.075 is found right here. We read up to this point. We read over to this point. And what do we have? Okay, K sub t is equal to 2. All right. We may as well, no, let's keep going with the flexural side. We'll get the flexural stress concentration done first. So what's next? Okay. This is the theoretical stress concentration factor. What do we want, you think? The fatigue stress concentration factor, which means we need to flip back to page 303, equation 632. Equation 632 says that K sub F is equal to 1 plus Q. What's Q? Notch sensitivity. The best way to find notch sensitivity is to first calculate your Newber constant. And from your Newber constant, you can plug that into equation 634 to find Q. The quick and dirty way to do it, if you don't need your results to be super, super accurate, is to read off of these charts. Okay? So my recommendation is, if you have a little bit of time to go ahead and do that, is to go ahead and run through that calculation. Otherwise, if you're trying to get a quick answer, use the chart. And since I'm more interested in showing you the rest of this problem, I'm going to go ahead and use the chart. Okay? So what's my notch radius? 0.03. What's my ultimate strength? 100 KSI. I end up right here, and if I read over, that looks to me, right here is 0.7. So I estimated this to be about 0.73. Okay. 0.73 times, I used 2 here, so 2 minus 1. And this tells me that my K sub F, this is for bending, this is going to be equal to approximately 1.73. All right, what next? Same idea, but for torsion. Okay.
What did we just use to find the KF? The chart,
This is a chart, figure 620. That is to find Q, which is notch sensitivity. All right, we'll use the same approach for the torsional aspect. Okay, we're going to let's see here, look for 0.075, read up to whichever of our curves is the highest for our capital D over D. So that's capital D over D equal 2, and reading over here, I estimated this as 1.58. And they call this K sub TS. The S that they put on the end of there just means shear. Okay, so what is K sub Fs? Okay, it'll have the same format, 1 plus Q sub shear, as they label it in the book. Q sub shear can be found from this chart. We again use the same 0.03 value for our notch radius, go up to our ultimate strength for the material, and read over. I estimated this to be 0.78. Correct. One is for shearing stress, one is for normal stress, right? And they sometimes kind of go back and forth between calling it torsion or shearing. Sometimes the notation's not always the same. All right, so we've got that, and then what do we put in here? We put in K sub T, which is 1.58, minus 1. And so K sub Fs is going to be equal to 1.452. All right, so we're just kind of taking care of business here, and we've got our stress concentration factor. What do you want to do next? Shall we get into the important stuff in the problem? I think that's probably a good idea to get there at this point. Okay, this is an interesting problem, and you actually have one on homework that's like this too, where instead of being given a load directly, what are you given instead? You're given deflections, and you know enough about the problem to be able to translate those deflections into stresses. Okay, so we're going to need a couple of values a couple different times here, so let me just solve for them real quick. What is the moment of inertia for the 0.4-inch diameter rod? Pi over 64 times what? 0.4 inches to the 4th power. And I get that this is going to be 1.257 times 10 to the minus 3 inches to the 4th. What about J, the polar second moment of area? Okay, same thing, but pi over 32 instead, right? So yes, 2 times that. And this ends up being 2.513 times 10 to the minus 3 inches to the 4th. Okay? And there's going to be a few places where we need that, so I figure I'll go ahead and put that in there.
Did you forget to do the export for the 0.4?
Yep. Thanks for keeping me on my toes. All right, so what we want to do now is we want to make an expression that relates how much force we push on this rod to how far it should deflect. Okay? And what's tricky about this is that there's a few different forms of deflection happening, right? And so let me state it kind of theoretically first. We'll say that let's call these delta 1 And over here, I'll call this delta 2. All right? Now, delta, more generally speaking, delta is going to be happening as a result of a few different deformations. One of them is due to the fact that the rod between B and C is going to deflect some. Okay? How much is it going to deflect? Well, we can, just that part of it. In other words, between B and C, that rod is not going to remain perfectly straight. It's going to actually curve some as a result of the load that's being applied. And how we can determine how that will happen is with our beam deflection tables that are in the back of the book. Okay? So I'll try to find those quickly. We have a plane cantilever happening there. And so that would be the very first case in table A9 on page 1021. The maximum deflection is going to be FL over 3EI. Okay, and I'll put down below, this is due to BC flexing. What else do we have? Okay, we got a twist that's going on. How much does that contribute? Okay, well, let's actually go ahead and define this and say, let's say that as a result of the load that's being applied, it might twist through some angle. Theta. If this is the only deflection that's going on, right, so we're treating each of these deflections similarly, this deflection's happening due to the fact that rod AB twists, right, because it's being held from twisting at A, but at B it's free to twist a little bit because it is flexible over that length. Okay, so that's going to be theta times what? Times 3 inches. Where does that 3 inches come from? Okay, that's actually, this 3 inches comes from the length of that rod, because what we're doing is we're using the definition of radians. We're saying that if theta is measured in radians, we can find, using approximately the arc length, we can find how far C has moved over. Right? Remember, the definition of radians is arc length divided by radius. We know the radius is 3 inches, so we take radius times angle, it gives us arc length. Yes. You guys are helping me out a lot here. Thank you. All right, so we have that, and then what? Yeah, so there's a flexure that happens between A and B. Okay, and that happens due to this F of t that's applied at B. Right? So really it's actually going to be the same FL cubed over 3EI, and this is due to flexure in AB. What about this piece right here? This is due to torsion, right? All right, so this is what we have to deal with. A couple of other quick comments. The L that we have for the first term due to BC, what L is that? Okay, that is the length of BC. The L that we have for the other term, what L is that? AB, right? They happen to have the same number in this particular problem. Just understand where those terms are coming from. All right. What about F? Is F the same for these two? Yes, it is, okay, because they both come from the F that's applied in this connecting rod. All right, what about theta? Does theta relate back to anything? Okay, what does theta relate back to? the torque, right? We actually have a formula for theta, TL over JG. But what's T? Okay, F times 3 inches times L over JG, right? F times 3 inches is the torque that's being applied on there. We said that a second ago. All right, so we actually can express all of this in terms of F. And since we know theta, or not theta, we know delta there. Since we know delta and we know all the other terms except for F, we can now solve for F. And in each of the positions that we have, where it's 0.1 to one side or 0.02 to the other side, and determine what our extremes are for that force that's being applied. All right? Shall we plug in some numbers? Okay, so I'll find F of t force extremes. All right, so what we'll do first is where delta is equal to 0.1. This is going to be equal to F times 3 inches over 3 times E. We wrote that up here. E is 30 times 10 to the 6th psi. And I, we found that here, 1.257 times 10 to the minus third inches to the fourth. And this F, and that should be cubed, right? Caught myself on that one. I knew probably 3 or 4 of you were waiting to ask me about that. All right. Now here's what's interesting. Is there going to be anything different in this other term for the flexure between A and B? Okay. There isn't, but only because these two lengths have the same value. All right. So don't do this if those two lengths have different values from one another, because it'll change this L. But since we have the same value, I can deal with that other length just by multiplying this by 2. Okay. And to this, I need to add theta times 3 inches. Theta is F times 3 inches times the L that we have in TL over JG. What L is that? It's the 3 inches that go from A to B. Okay, so let me actually kind of note these. This is torque. This is the L of TL over JG. J is down here, which is 2.513 times 10 to the negative third inches to the fourth. And G is 11.5 times 10 to the 6th psi. Okay, so that's J, and this is G. And then what am I going to do with this as well? Multiply by 3 inches. That came from the 3 inches that we had originally due to basically coming up with that arc length based on the angle.
Why wouldn't there be like 2 angles, like AB getting...
Because we're dealing with movement of B, we're basically looking at how far B moves. We're getting that with the flexure equation for AB, right? It also twists at B. That's what we're getting with this term, right? Then we multiply it by that 3 inches to get what that twist implies as far as how far C moves. And then to that, we're going to add an additional amount of movement of C due to the fact that between B and C, that part also flexes. Okay? All right, so this is all an equation that is set up in terms of f. It's our one variable, which means we can solve for f. And so that I don't bore you, I won't actually punch those in and solve for them. What I do is I get 70.84 pounds. Okay? And one thing that's kind of important to note here is what direction does that push? Right? This problem would be different if the two positions were both in the same direction. But our position actually goes to two sides of equilibrium. Right? So I'm going to go ahead and make a note over here that this, goes to the right. Okay, and I know we haven't really formally defined right and left, but it looks generally to the right there. Okay? So what do we do to find the other direction? All of this again, nothing changes except what? So we change that to 0.02 inches and calculate again. And the F that we have there is going to be equal to 14.17 pounds. And that goes to the left. Good so far? All right. Well, now what? Okay, we're actually to a place now where it should be a little bit easier for us to put this in terms that we know what to do with it. Right? We've handled the deflection side of it, gotten forces. Now we should be able to get stresses. Okay. All right. So, normal stress. Which, by the way, where is your worst case patch going to be? Yeah, you actually probably can't see it. It'll be back right there. Okay, how do I know that? Yeah, that's where you have the worst amount of tension happening due to this flexure, right? As far as torsion, there's no one spot that's any worse than the others around the entire circumference of the thing as far as the torsional aspect. But for the flexure aspect, it's going to have its worst case stress when this thing is pushed to one side like that. So, and it'll be on that back side. That's not really part of our question that we need to answer per se, but it's something that's always good to think about. Where is this actual location of material where we have our worst case? All right, so what is this going to be? Well, we need to figure out what the bending moment is back there at location A. Okay, how do we do that? Okay, just F times 3 inches. Right? Because we don't have to worry about all the rest of this stuff. We're dealing with the rest of the effect of this force with a torsion that happens at B. We're really looking at the case of applying this load right at B. So we multiply that by 3 inches, and we get a flexure that happens around location A, or a bending moment that happens around location A. Okay? And so this is just going to be equal to whatever our F values are, times 3 inches. Okay, that gives me M. I'm using MC over I right here. What is C? Okay. And I, we've already calculated that, 1.257 times 10 to the minus third inches to the fourth. Okay. And so what's our maximum stress? We'll just plug in that 70.84. Pounds times 3 inches times 0.2 inches over 1.257 times 10 to the minus third inch to the fourth. Okay, and what we get there is 33.8 KSI. What about my minimum normal stress due to flexure? Same thing, but now what I'm going to do is say negative 14.17 pounds times 3 inches times 0.2 inches. All this divided by 1.257 times 10 to the minus third inch to the fourth. And this gives us negative 6.76 KSI. Okay, why do I have positive and negative here? Okay, yeah, it's flexing in opposite directions. Okay, you push it one direction and pull it the other direction. It means that those stresses, whatever they're doing in that material, it's reversing the process. And so I need to go ahead and make sure those values have opposite signs from one another. All right. So these are actually, by the way, these are nominal stresses. And we'll leave them that way for right now. Let's find our nominal stresses that we would have for the question of torsion. Our equation for torsion is going to be what? The torque is going to be F times 3 inches. Right? The equation itself that we're going to be using here is TC over J. Right? And so what we'll do here is we'll do TC over J, where T is F times 3 inches. What is C? Again, 0.4 inches over 2. J, we found earlier. 2.513 times 10 to the minus third inches to the fourth. All right. So what's our max? 70.84 pounds times 3 inches times 0.2 inches all over 2.513 times 10 to the minus third inch to the fourth. This is going to be equal to 16.9 KSI. The minimum stress is going to be the same idea, but minus 14.17 times 3 inches times 0.2 inches over 2.513 times 10 to the minus third inch to the fourth. And out of that, we get negative 3.38 KSI. What now? Okay. We need to do a couple things. One of them is stress concentration factors. Actually, I tell you what, let's go ahead and take a peek at the equations that I referenced earlier. Those equations are on page 326. They are equations 655 and 656. What you'll notice is that these equations build in your stress concentration factors. So if you want to use these equations, you want to actually find your mid-range and alternating stresses. I guess if you want to use them directly, you want to find your mid-range and alternating stresses as nominal stresses, not as fully computed maximum stresses, right? Because it has those incorporated into these equations instead of doing them separately. Okay? For our problem, one of the things that you'll notice there is that they have it set up to where they have a component for bending, a component for axial, and a component for torsion. And we have bending and we have torsion. Do we have axial? Not for this problem. What would the only thing have been that we would have needed to change if we'd wanted to create a problem that had axial? Okay. What if I took the direction of this cyclic load and instead of making it in that direction, I actually changed the direction a little bit and put a component of that load that would be parallel to the direction of AB? That would actually have created, would have done two things actually. It would have made an axial load in AB, but what else would it have done? More flexural components to things as well. That would have complicated this problem significantly, because we would have had to handle all of those deflections as well, right, in the first part of the problem. So it's one of the reasons I chose not to do that. But that's, giving you a reasonable scenario where you could end up with an axial load in one of these things. All right. So, yes, we want to find mid-range and alternating. Okay. Let me do that right here. What is my stress mid-range going to be? This may not be a good place to do it. I'm going to run out of space right there pretty quick. Okay, I'll move over to here to the side. What's my mid-range stress? It'll be 33.8 KSI plus a minus 6.6 or 6.76, excuse me, KSI over 2. And so that gives me a mid-range stress value of 13.52 KSI. What about my alternating stress? Same thing, but what do we do? Okay. Minus a minus 6.76 KSI over 2. And so my alternating component of normal stress that happens at my critical patch is going to be equal to 20.28 KSI. Mid-range shearing stress, the same kind of idea here, is going to be equal to 16.9 KSI plus a minus 3.72 3.38 KSI over 2. And that value is 6.76 KSI. And my alternating component of shearing stress due to torsion is just going to be 16.9 KSI minus a minus 3.38 KSI, that over 2. And that gives me 10.14 KSI. We now have mid-range and alternating stresses. What else do we need? Well, at this point, if we want to actually use equations 655 and 656, we can do that because we have our mid-range and alternating components for each of the types of stress that are happening. And we can now plug those into equations 655, 656 to get what they call, these are sort of our von Mises mid-range and alternating stress, right? All right, and so what we have there is we plug in our stress concentration factor. That's what you see for bending there. That was 1.73 multiplied by the alternating component, 20.28 KSI squared. Okay, we can ignore the axial component. Okay, so I've kind of already done that. Plus 3 times, that's part of our von Mises stress calculation, 3 times our K sub Fs. K sub Fs, remember, was 1.452. This gets multiplied by our alternating component of torsion, which was 10.14 KSI. Take all of this stuff and take it to the 1/2 power. Yes. Thank you. This is for all the alternating component. I switched gears after I wrote the label on there. All right. So our alternating component there is going to be equal to 43.37 KSI. Okay, the mid-range component looks very similar. We put in 1.73 times. Now we need our mid-range component of bending stress, which was 13.52. KSI. This will be squared. We add to that 3 times stress concentration factor for shear, for that torsional component, multiplied by the mid-range component for shear. That will be squared, and we take the square root. And once we've done all of that, we get 28.92 KSI. So it's worthwhile now looking back at our equation and seeing what do we need. Okay, we're using an equation here that's on page 316 for ASME elliptic criteria. It says fatigue factor of safety, N sub F. It's going to be equal to a square root of 1 over sigma A. Okay, what is sigma A? 43.37. KSI over, oh shoot, S sub B. Okay. I'll leave that blank for right now. Okay. 28.92 KSI for our mid-range component over S sub Y, and S sub Y was up here at the top, 84 KSI. We're missing fully corrected endurance limit. Okay. What sorts of things do we need to correct for? Okay, surface finish is 1. What kind of surface finish is it? Machined. That means I can take K sub A equal to 2.7. Where do I get that number? Okay, this comes from table 6.2. And the exponent up here will also come from table 6.2 to the negative 0.265. Okay, this whole equation is equation 619. And what we get out of it is the surface factor is going to be 0.797. Okay? It's going to go through some that we don't need to use. We are not dealing with temperature. We're not dealing with any sort of statement about what we should do for reliability. If you're not told anything, even though this seems kind of weird, you can assume 50% reliability. Okay? Meaning that you're just right in the middle of the data. Okay? So we don't have those. What about loading factor, K sub C? Okay. Direct your attention to this, this section in the book. It tells you in here that you will not use a K sub C factor when you are using these von Mises equations. Okay. If you're using the von Mises equations, they incorporate already any sort of a loading factor that you may have had in there. Okay? So do not use a separate K sub C when you are using your von Mises form of the mid-range and alternating stress equations. Okay? So what are we left with? Size factor. This one requires a slight miniature discussion. We have two things going on here. One, we have a pulsating torsion. What does that do to the stress? What's the stress profile for your maximum stress look like? It's like a donut, right? Your maximum stress due to torsion is going to be around the entire perimeter. What about stress due to flexure? It's going to be 2 slivers on each side. Right? 1 sliver on each side. Okay? So what do we do for size factor? Do we need to account for the idea of non-rotating bending, or do we not need to account for that? What do you think? Well, here's a question. Which is worse? Which of them is more conservative or less conservative? So I would actually say that if you understand what the size factor does, the size factor basically accounts for if there's more material or less material that ends up feeling your highest stresses. Okay? What we actually have here is a situation where that whole entire donut may not feel all of those high stresses, but we could conservatively say that it does. Right? And the book doesn't actually give us guidelines on what to do in this situation. So I'm going to tell you what I want you to do, okay? And this is not a bad thing to do, right? I will tell you that it's a more conservative thing to do, go ahead and treat it as if it is rotating bending, even though it's not. Because the torsion side of it does behave that way, right? The bending side doesn't. So you're kind of trapped in the middle. The more conservative thing to do is to pretend like it is all rotating bending and not sort of expect that you get this benefit of having less material that goes to those really high stresses. Okay? So, having said that, that's actually a good thing because it makes this easy for us. All we have to do is plug into equation 620 our diameter in inches over 0.3 raised to the negative 0.107. And this gives us 0.97. And these are the only two Marin factors that we need to use for this problem. All right? So our fully corrected S sub E then is going to be equal to 0.5 times 100 KSI times 0.797 times 0.97. And our fully corrected endurance limit then is equal to 38.66. KSI. And what's our factor of safety? Come on, you can't do that in your head? All right. The factor of safety comes out to be 0.876. Which begs the question, will it last forever? It will not, right? We do not predict that this is going to have infinite life. What would we do to go back then and figure out how long its life really is? Like if I say, okay, this is less than 1, I wouldn't predict it has infinite life. That means I should be able to predict how many cycles it can last before it breaks, at least a rough guess. Okay, what do I do? Moving right into that, let me graphically show you what we're going to be doing here, okay? And I'm going to do this on our mid-range and alternating stress axes. Okay, so if we plot our mid-range and alternating stress like this, the point where we would have failure is represented for this particular problem with ASME Elliptic. It's represented with an ellipse that does something like this. And I won't try to plot it exactly, but let's say you have a little portion of an ellipse that is set up like this. The point up here, if we're designing for infinite life, is our endurance limit, our fully corrected endurance limit up there. And then down here, we have our yielding strength. Okay, and I haven't plotted our points exactly. Let's see, we have, trying to remember what our different values were. Alternating 43, mid-range 28. So that means that we're probably going to have a slope for our load line that is more vertical than it is horizontal. Do you agree with that? Something like this. And it's going to be outside. How do I know it's outside? Factor of safety is lower than 1, right? And so if my factor of safety is lower than 1, that means that my point that I plot on these axes is going to be outside of that curve, okay? So actually the first step of figuring out how many cycles we expect to happen here is we have to come up with some way of establishing what the equivalent amount of fully reversed loading is for the type of loading that we actually have, because we don't have fully reversed loading here, right? We have some arbitrary type of load where we have a certain mid-range, a certain alternating component. And so what that involves is basically fitting another curve like the ASME elliptic ellipse through our point that we actually have so that we can find a point here that we call S sub f. Okay? S sub e is kind of like a special case of S sub f. Okay? S sub f is our fatigue strength. S sub e is the fatigue strength for a case where we have infinite life. Right? If we have a stress that's larger than that, then that stress that's larger than that probably is going to indicate that the life will no longer be infinite. And so our first step of our process here is to take the equations that we had for our ASME elliptic, which I'll find those here real quick. Let's see. On page 314, ASME elliptic equation basically says that we have S sub A over S sub E. But what we're doing here is we're going to replace S sub E with S sub F. Okay? Because what we're doing is we're not using the case where this curve comes up and hits S sub E. We're using where it comes up and hits some larger strength value that implies a non-infinite life. So we have S sub F here, and this is going to be squared. And we have S sub M over S sub Y squared, and this is equal to 1. Okay, and if you want to know what equation this is on page 314, equation 643. Okay. What you basically have here is that your SA and SM are the coordinates of this point right here. SM, SA. Okay? And what we're using is the coordinates of those points, or that point right there, to be able to back solve for SF. All right? So graphically, that's the interpretation of what we're doing. So what we'll do here is we'll go ahead and move this to the other side of the equation. So we would have SA over SF squared is equal to 1 minus SM over SY squared. And then we take the square root of all of this. Like so. And what we end up with when we solve for SF is we are going to have SA over this square root of 1 minus SM over SY squared. Okay. How do we use this? Well, we plug in our values for sigma prime A and sigma prime M in for SA and SM. We plug in our value for yielding strength into SY, and we solve. Okay, so we'll go ahead and do that. SF is going to be equal to, sigma A there was 43.37 KSI. We'll divide this by the square root of 1 minus SM, which we're plugging in sigma prime M for that, 28.92 KSI over SY, and SY, I believe, was 84 KSI. Okay, and when we plug these things in, the SF value that I get is 46.19 KSI. Okay, so as review, how do I interpret that? What does that number mean? This is basically the fully reversed stress magnitude that I would have to basically be an equivalent to this mid-range and alternating stress that I had before, right? This is equivalent in terms of how much damage it would cause according to the ASME Elliptic criteria, okay? It would be different if we used a different criteria, right? But if we're using ASME Elliptic, then this is how these are related. All right, well, what do I do with that then? Okay, we have to flip back to page 293, that's where we have our relationships between number of cycles and stress levels. And if you look at an equation, for instance, like 616, it says that the number of cycles is going to be equal to the stress that they call it sigma sub rev. What that basically means is it is that fully reversed stress value over A, all of this raised to the 1 over B. Well, how do I know what A and B are?
What equation is this?
This is equation 616. Well, A and B are shown right above it. A is going to be equal to F. What is F? Okay, F, remember, is the fraction of your ultimate strength where the curve that tells you the number of cycles. I think I actually have that over here somewhere. Down here. Remember, F is the fraction of where this curve kind of breaks over right there, right? Fraction of SUT, and it's something that is purely a function of ultimate strength, according to the procedure that's shown on page 292, right? So they have that whole procedure on 292 encapsulated into a single chart over here where we can look up F based on the ultimate strength of the material, which means I got to go back over here because I don't remember what that was. Ultimate strength of the material was 100 KSI. So we go down here and read off of this chart 100 KSI. It's roughly right there, and so I picked off a 0.845. And keep in mind, if you want more accurate values of F, you can always get them by repeating the procedure shown on page 292. A lot of these problems I go ahead and use this chart because it's a quicker way to get it. All right? So 0.845, and we can use that way up here to find A, 0.845 times S sub UT, which is 100 KSI, all of this squared, over S sub E, and that's our fully corrected endurance limit, which I had up here, 38.66 KSI. Okay, and this is equation 614. Okay, that expression right there gives us 179.18 KSI. That's my A coefficient. B is just going to be equal to minus 1/3 log base 10 of F times 100 KSI over S sub E, which is again 38.66 KSI. All right, and calculating these gives me negative 0.1088. Okay, so how do I find my number of cycles I expect to be able to withstand? Well, I've got everything I need now. N is going to be equal to 46.19 KSI over A, which is 179.18 KSI. All of this raised to the 1 over negative 0.1088. Which is around 258,000 cycles. Yes, sir. Right. If it becomes lower strength materials, S sub UT values less than 70 KSI, it recommends that you let F cap out at 0.9. Because you'll notice on that chart, it's getting larger and larger as you move to the left, right? Oh, not that one. This one right here. And what they're basically saying is for any values that are further to the left from here, basically the way they're saying to treat this curve is have it cap off right there.
I just remember for a certain homework problem, I found that was equal to 1 point something the other way.
I'll need to check that out. It's not supposed to be that way, and I apologize if there was one that was messed up. So thanks for bringing that to my attention. All right? All right, all right. Any questions? This, by the way, that equation I did, 616, it's just a rearranged form of equation 613, which is S sub F is equal to A n to the B. Okay? Those are not different from each other. They're just basically rearranged to where you're finding cycles rather than finding, strength. All right? All right.